All right, we're live. I was about to say good morning, but it's more like good afternoon. Welcome to this, kind of second Spring Framework 5 session after my quickie yesterday. This is actually the one that covers the more strategic themes, so they came kind of in inverse order. There's also, of course, a connection to other talks you might have seen today, like the Spring Boot to the Dough talk or the Reactive Spring talk. All of those topics really center around what Spring Framework 5 started and what Spring Framework 5 provides the foundation for. I'm going to use a bit of a different spin here. So from my everyday role, leading the actual Spring Framework open source project, I'm not only intimately familiar with the challenges that we're facing today, it's in particular my job to plan for the next iterations, for the next 12 to 18 months, anticipating where the industry is going, anticipating other critical infrastructure releases that will be released in that time frame, and how our schedule may react to that. When are we going to pick up those things? Can we do forward compatible measures up front? So all of those challenges, in this industry, are never going away, right? There's always just the next iteration. So what I'm going to talk about today is what we've been choosing as the themes and recognizing as central trends in the industry for Spring Framework 5.0. I'll hint a little also how we are going to address the challenges of 2018. But ultimately, we realize that a major release that we are bringing to the mainstream now, like Spring Framework 5.0, generally available since September now, those kinds of releases they need to be prepared for the challenges that you are facing, that we are facing, and that you are facing in next year, really, when actually many projects out there are going to build on this generation of the framework. So much for the 2018 plus part, right? All right. So just summarizing the hopefully well-known facts. This is basically the fact sheet, right? So Spring Framework 5.0 is GAs in September. It's JDK 8 baselined. So we took the opportunity to revisit the entire code base and make it Java 8 plus in terms of its assumptions. So it may use Java 8 API features and, of course, language features in the core framework code base now. That wasn't possible before because, if you remember, Spring Framework 4, even for the 3, is still JDK 6 compatible, JDK 6, 7, 8. It has lots of JDK 8 support. So if you're using Spring Framework 4.3 on JDK 8, it's going to feel like a Java 8-based framework to you in many ways, and almost comprehensively, right? You're hardly going to notice that it's not Java 8-based. But there are a few things that we can only do when the framework itself internally can be built and designed on Java 8. And for the 3, we're constrained by what we can do at runtime. Detecting the use of Java 8 constructs in your code, reacting to it at runtime in your code. So that was fine, provided a lot of value, but this is a measure that we have been looking for a lot, right? And it's also showing some value that we're going to notice in a few places. We can start using Java util function, completable future, other API types in Java 8. In our core contracts, core API contracts and core SPI contracts now. So this Java 8 plus baseline is actually a pretty important step for us. It's also the reason why we skipped the JDK 7 baseline, right? There's no Spring Framework generation that is JDK 7 plus. We went from 6 plus to 8 plus straight away. All right, at the same time, it's basically a Java E7 baseline in the corresponding specs. So Servlet 3.1 plus, Bean Validation 1.1, JPA 2.1, basically the 2013 Java EE generation of specifications is the minimum that we require now if you're integrating with providers of those. And we have support for JUnit 5, but not quite as a baseline yet. It's in parallel to JUnit 4.12 support, but definitely check it out. I mean, JUnit 5 was a long time coming. It's really worth having now. We've also been part of the group that sponsored the JUnit 5 effort last year, so we've been really interested in making it happen and immediately picked it up with 5.0 GA here. So that's the whole baseline, the minimum requirements. At the same time, there's no coincidence here. Spring Framework 5.0 went GA in September. shortly after JDK 9 and shortly after the Java EE8 specification, so shortly after Servlet 4.0, JPA to the 2, bean validation to the DO, and co. So we aligned with the timing of those. Initially, we planned actually to go live a little bit earlier, but it worked really fine for us in the end. All right, so that's kind of the general story. Let's pick a few themes that we dive into a little bit more. And in particular, I'll give you a bit of a background on not only the what, but in particular the why and our recommendations around it. All right, so a central theme was JDK 9. JDK 8 is a baseline, the common JDK out there for years to come for sure. A new JDK available to us, JDK 9 right now. And JDK 9 is a particularly critical, almost radical release, since it restructured so many things within the JDK. Lots of tooling had to be updated. And of course, there are plenty of features in JDK 9. There's actually a ton of features that has nothing to do with Jigsaw at all, right? We'll get to Jigsaw in a moment. But JDK 9 is a sum of many features that are really worth having in the end. Many runtime features, the garbage collection refinements, G1 is the default now, and HTTP2 ready TLS stack out of the box at the JVM level. The compact strings feature, collection factory methods, map off, set off, list off, those are all really nice features, and there are plenty of them. So even if you don't care about Jigsaw, if you care then stay tuned for a moment, but even if you don't care about Jigsaw, generally consider the upgrade. Try the upgrade. If you're using the latest framework versions of not only Spring, but also say Hibernate and Mockito and co, you might have a pretty smooth experience upgrading to JDK 9. So just know where you are. In terms of production, it's a little bit of a different matter, of course. JDK 9 is not a long-term support release. So if you're embracing it right now, you will have to upgrade to be on a supported branch in March 2018 already on JDK 10, and once again in September 2018 onto JDK 11. Which is the next long-term support release, the next JDK 8-like support release, right? So from our perspective, that means that in production, lots of people are going to wait for JDK 11. But there is an intermediate path. Try the upgrade, Spring framework, and everything that we have an influence on around us is perfectly ready. The Spring framework build itself, by the way, if you've been a contributor, maybe sent a pull request to Spring framework or created a custom fork for any reason, Spring framework itself, the build, runs on JDK 8 and 9. The entire test suite can also pass on JDK 8 and 9, even at this point already. And in case you're wondering, Spring Framework 4.3 is not explicitly JDK 9 aware, but we've backported everything that's necessary to make Spring Framework 4.3 applications run fine on JDK 9. Even if there's no explicit support, right? No ESM version that understands module infos or anything else, but it actually works fine on the class path and to a very large degree even on the module path without explicit measures, just fine-tuning some of its behavior to be JDK 9 forward compatible. But the build, of course, and all the special measures are only in Spring Framework 5.0. All right, the Jigsaw topic is... It's a very significant step being taken at the JVM level. For the first time in the JVM's history, there's an alternative to the class path. This good old thing that lists a very long number of potential directories and jar files that the JVM can find classes and resources in. It's a really almost awkward mechanism, really, if you think about it. But it worked fine for such a long time. In JDK 9, there's the module path, a much more controlled way of deploying, essentially, jar files to the JVM. So by putting the very same jar, not onto the class path, but onto the module path, you're basically opting into the Jigsaw rules, the module path rules. Every jar file is going to be kind of wrapped with a module into a module at runtime. The JVM actually retains the understanding of the structure of what you deployed. So in contrast to the class path, where it's just directories and zip archives, basically, and the JVM knows nothing more about this at runtime. In the module path world, it understands that there's a Spring Core module, there's Spring Beans module, there's Spring Context module. It knows the boundaries of those modules, certain visibility rules, the names of those modules, the interdependencies between those modules. That's a really clever way of optimizing the runtime representation of the archives that contain our classes and resources. Once you go onto the module path, be aware that essentially you have to deploy everything that you're using onto the module path. Your application jars, the framework jars that you're using, and all the dependencies of your framework jars. This works reasonably well with the current generation of open source frameworks and libraries out there, at least the ones that we tested. What we're doing in Spring Framework 5.0 is that we're actually declaring automatic module name manifest entries. So the jars that you get when you download Spring Framework 5.0 from Maven Central basically include a well-defined module name that is being ignored on Java 8. And in Java 9, the compiler and the runtime understands that this is the canonical module name of this particular jar file. Otherwise, if such a header is not being provided, the name is derived from the artifact name, so like spring-core-5.0.2.jar. It would drop the version number, replace the dash with a dot, and you end up with spring.core, which is actually the module name that we've chosen, right? It is the name that we're declaring in automatic module name in the automatic module name header. The difference is you may rename the jar files, and the module name remains stable. Right? So we are providing stable module names as of Spring Framework 5.0, but even in 4.3 you simply have the file name derived module names. Works just as fine really if you don't rename the archives. So from an application perspective, and that's the whole point in the end, right? Why would you care about the module path? Well, for validating what you deployed, right, so that there's no overlap in the packages declared in those jar files, there's a bit of validation that comes with the module system. But that's only really a small benefit. The much bigger benefit only comes in when you start shipping module descriptors in your jar files, right? When you are opting into the module system in your application code base. So an application might ship a module info.java that just has a name right attached and requires, for example, the Spring JDBC module, implicitly gets the Spring Core module underneath. The same can be done with not only the Spring modules, of course, but any other open source modules. This is a really nice descriptive way, in the end, and a concise way of representing the dependencies very explicitly that each of your application modules has, right? So this is the benefit that we intend to provide. This is what we're focusing on. And for that benefit to be available to you, we are already doing everything that's technically necessary. So it is not relevant for your purposes whether the framework itself is a JDK 9 Plus framework or includes module info class files. It doesn't matter really. The only thing that matters is that you can syntactically do what this sketch illustrates in your application modules, and that's entirely possible already. So this is the reason why we chose this compromise to keep the framework JDK based, but provide the full basically module system value for your application modules if you opt into JDK 9 and if you opt into the module path on JDK 9. All right, keep in mind, you can happily keep using the class path on JDK 9. The easiest way of upgrading is take your existing JDK 8-based application, set Java Home to JDK 9 and run it, right? There's no need to opt into the module path. Consider wisely whether you go through that exercise, right? There's some pain waiting for you. If you want to avoid the pain for the time being, or even kind of strategically, you might want to stay on the class path. And if you don't have any issues with the class path in particular, right? All right. There's a related topic that I find much more important, and that's HTTP 2. For some reason, in Java land, we seem to be having some trouble embracing HTTP 2. I mean, I'm not going to go into too much details about the protocol itself, but keep in mind that this is the first major revision of the HTTP protocol in 20 years. I mean, overdue is an understatement, right? It provides so many benefits, in particular wire-level benefits, right? Like the binary representation, connection multiplexing, headers compression, like sending a sequence of requests and just saying, yes, the same requests as before, essentially, not repeating the entire text representation of all your headers in every single individual request. All of those things are so worth having, and are actually transparent benefits. Fortunately, the traditional Java way of building web applications doesn't really have to be revisited much at all for HTTP2. The servlet abstraction doesn't need any changes at the servlet API level in order to have HTTP2 underneath the covers. You can run an existing servlet-based application, Spring Web MVC-based application, very easily on an HTTP2-ready web server setup, and you transparently get HTTP2 benefits for clients asking your server to talk HTTP2, right? But that's not the norm in Java land yet. Most of our Java-based servers downgrade those clients to HTTP 1.1. They don't let them upgrade to HTTP 2 because they are not set up for it, right? HTTP 2 in particular really focuses on secure connections. In the HTTP 2 world, that means a TLS stack that needs to be ready for HTTP 2, and that is essentially the problem. In Java 8, there's no out-of-the-box stack for those purposes. So there's Servlet 4.0, you might wonder, right? We have it since September. Isn't that HTTP 2 ready? Well, yes, sort of, right? It was designed with HTTP 2 in mind, but it doesn't actually require HTTP 2. And the real challenges do not lie in the servlet world. What Servlet 4.0 did is absolutely fine, right? It's worth it. They introduced a push builder API, having this one specific feature where you can programmatically trigger pushes of additional resources to an HTTP 2 client. That's fine, but frankly, it's probably the least interesting feature in HTTP 2. It's the one where it's also unclear when you're even supposed to do it. It might be better to leave that off to some heuristics at the web server level anyway. All the other benefits in HTTP 2 are way more important. So Servlet 4.0 doesn't really bring much to the table here. Servlet 3.1 containers are essentially fine for having HTTP 2 underneath the covers. The problem is more to be found in the actual servers, in the actual containers. And surprise, surprise, the current generation of Servlet 3.1 containers actually comes with HTTP 2 setup options. In Tomcat 8.5, in Jetty 9.4, in Undertow 1.4. They are sometimes a little bit out of the ordinary what you have to do, right? You have to modify your JVM installation, usually put stuff onto the boot class path or set up the Tomcat native up front. It doesn't come for free, and it's not just a flag, right? You really need to set up your installation accordingly. But it is doable with all three of them in their current generations already. They are all Servlet 3.1 based, except for Tomcat 9.0. Tomcat 9.0 is GA, by the way, so the first Servlet 4.0 container out there in the wild, production ready for about a month. But all the others are Servlet 3.1 containers, but can still be set up for HTTP 2. By all means, consider this. At least familiarize yourself what it would take to enable HTTP 2 in your systems. And if you can choose a Servlet 4 container like Tomcat 9, even better, but not actually a mandatory part of the HTTP 2 story that you might want to achieve, right? So Servlet 4.0 is the bonus. The necessity is HTTP 2 underneath the covers. All right. And of course, to make the connection with JDK 9 here, in JDK 9 you have a TLS stack out of the box. So running Tomcat 9 on JDK 9, or even a JDO Undertow on JDK 9 might be a significantly more streamlined setup than you might have on JDK 8. But then comes the support question, right? JDK 9 is a feature branch, not a long-term support branch yet. So by all means, if you want to do this in JDK 8 in production, try it. There are ways of achieving it. They might not be super nice, but it's doable. And in Spring Boot 2.0, we started having explicit HTTP 2 setup options out of the box. We can't do everything for you, but we're going to smoothen the path to enable HTTP 2 in Spring Boot-based deployments for you. And Spring Boot 2.0 is about to enter its release candidate phase and going GA towards the end of this year. All right. Switching gears a little. In Spring Framework 5, a very essential topic at the API level is functional API design. You might wonder, functional? What do you even mean by functional? Well, it's functional in the sense of Java 8 functional, right? Functional API as in Java util collection streams on JDK 8. That sort of functional, right? Functionally styled APIs with a heavy use of lambda expressions and method references. That sort of API design is what we mean here. Traditionally, of course, we had a strong focus on annotation-based components. This remains true, right? So even in Spring Framework 5.0, there's a strong focus on annotation-based components. It's very first class, but also very complete already. So to some degree, we wrapped up all the loose ends in that story in Spring Framework 4.3. There's really very little left that we intend to add to the annotation-based model, fundamentally. So from that perspective, we really took inspiration from functional API design for Spring Framework 5, kind of revisiting the challenges, the tasks that you want your framework to allow for, right? To get the setup options, the registration needs at the core container level or at the web framework level. We revisited all of those topics from a functional API design perspective, which basically conceptually means no annotations, just to take a position, right? Say like, there's the annotation story, let's try something different. No annotations, ideally no reflection, no class path scanning. So to have an extreme position that allows for a lot of fine-tuning and a lot of gray in between. Right? Of course, in practice, you can mix and match the annotation-based and the functional registration mechanisms. You can use class path scanning to some degree. You will use reflection if you want to do annotation-driven interception or point-get-driven interception without waving, right? So we are not being extreme here. We're just trying to explore our options and to force the core container design and also our web framework design to be able to accommodate not only the annotation-based story, but also a purely programmatic functional registration story. This required actually quite a few measures, more than might initially appear at the surface. There are a few new registration methods, of course, but there's also lots of internal work. The core container is very efficient in creating instances based on instance suppliers, for example. We are not trying to bridge this anywhere. It's a very straight line. So we are not only trying to allow for this API model, we are trying to embrace that model to the degree of very efficiently handling it at runtime. A measure that is sort of related to this is a topic that I touched upon yesterday. It's also being touched upon in the Kotlin talk yesterday, is nullability. So we revisited the entire code base and have very strict and clear nullability declarations on all Spring method parameters, Spring API method parameters, and return values. So instead of just having some wording in the Java doc, there's now a formal nullable declaration for every parameter and every return value that is actually nullable. This is enormously helpful, in particular in programmatic API design, in particular in combination with Kotlin, where the Kotlin compiler, as Kotlin as a language kind of being a very suitable choice for functional registration mechanisms to begin with, right? And kind of trying to be as friendly and as comprehensive as we can towards the Kotlin compiler. The Kotlin compiler can make really good use of clean nullability declarations, allowing assignments to non-nullable variables and so forth. So that's the other part where Kotlin actually comes into the picture first here. Even at the core container level, we ship Kotlin extensions. We're going to see this in just a moment. So what does this mean concretely, right? And I'm just going to illustrate what this can mean, right? There are quite a few ways of accomplishing such a setup. But fundamentally, you can start at a very low level, right? Take a generic application context in Spring. That's the good old generic application context that also has scan methods and whatever on it. and register methods for annotation-based classes that you enumerate. But it now also has explicit register bean methods, which are designed for a functional style, right? So, for example, the little sketch above says we're registering a foo class with default conventions, basically calling the default constructor. We're registering a bar class, and there's a callback, which is actually a Java util function supplier of bar, and specified as an inline lambda expression, right? So this little line here is what we call an instance supplier, a Java lambda compiled against the supplier, being stored in the bean definition. Every time the container needs a new instance of bar, it's going to call that instance supplier. It's not going to use reflection to choose a constructor and invoke it. It's also not using factory methods, like admin methods. It's dispatching to this instance supplier, which is technically not using reflection. It's an invoke dynamic dispatch straight to your code. The example below is a little more extensive, has a few interesting twists that are worth discussing. It basically does the same thing. It adds a lazy init. It basically assumes this is a singleton bean and adds a lazy init flag as well. But otherwise, it's equivalent. But look at the register bean foo one. What do we do here? We say foo new, right? Might look a little alien. It's a Java 8 method reference, right? It's basically a symbolic reference, a compiler reference, to the default constructor on the foo class. The difference is simply, in this case, we are not going to use reflection at runtime, because this is an instance supplier, a Java 8 method reference bound to a Java util function supplier that we are dispatching to directly. No reflection involved. Because technically, even class new instance is reflection, right? Reflectively calling the default constructor on that class. So just a twist, right? If you really care about those things, you can be very explicit even in this case, in this simple case. Below, there's the instance supplier, but there's a second line. And this is the aforementioned lazy init flag, right? We call this bean definition customizers. There can be any number of those. Basically, typically one-line expressions. The resulting bean definition that is being registered with the Spring Core container coming in, and you can fine-tune any of its characteristics. This is the same programmatic registration mechanism that has been in Spring for 10 plus years. So it's the same bean definition model. Any tools or any setup code you might already have that fine-tunes bean definitions could even be invoked here. All right, so this is fundamentally our idea of functional bean registration. Now imagine a smaller microservice with an innumerable number of components, right? A reasonable number, say 5, 10, 15, 20 components. It's still feasible to configure them like this. You may also mix and match this with scanning. You can also register some components this way, additionally scan for annotated components. You can use annotations on those classes. If you choose an annotation config application context, or otherwise activate the annotation config features in this generic application context, you may also have this setup code, but the classes like foo and bar that you're registering internally declare some annotations. No problem with that at all. All right. Now, this is the Java 8 style of doing this. There's a few interesting examples, and I've only picked two as an illustration of how to accomplish this with Kotlin. This is basically the same code. The same code being called from a little piece of Kotlin code, where you're instantiating the generic application context, registering the foo class, and registering the bar class with an instance supplier. Now, let's revisit the code before, right? We're saying bar.class and an instance supplier. Whereas in the Kotlin version, we are just providing an instance supplier. It's a simple explanation for the difference. In Kotlin, we can actually make assumptions about the generics declared by such an expression. In this case, kind of the return type of a function. In Java 8 Lambda expressions, we can't. So up front, if we're dealing with a Java 8 Lambda expression, we, from the outside perspective, do not know what that Lambda expression will produce once invoked. So up front, we have to get some extra information, what type it will actually be, because that's really important for the core container to know. So that is the reason why we're registering, why we're specifying an explicit bar argument and an instance supplier. In Kotlin, that's not necessary because Kotlin functions have a runtime API for proper introspection of the return types, basically reified generics, allowing this register bean invocation to make a clean and reliable assumption about the actual bean type without an extra parameter. So that alone shortens it quite a bit, right? The code below is kind of equivalent to the code above, but uses a different syntactic arrangement, kind of inline invocations here instead of the more traditional Java-style invocations. I've been dubbing this Gradle-style usage. The Gradle style, take it with a big grain of salt. It's basically because the Gradle DSL, the Gradle Kotlin DSL, uses a similar structural arrangement. Well, it's quite interesting in what you can do here. Kotlin has a few variants that all make total sense with these registration APIs. And the reason why this code is even possible is that we are shipping Kotlin extensions in several of our jars. So when the Kotlin compiler is being used with the Spring Context jar, the Kotlin compiler picks up certain extensions, like generic application context extension.kt. It automatically picks them up, files that are part of our standard jars that you can get from Maven Central, but only the Kotlin compiler understands them. Basically like module info descriptors in JDK9 only being understood on JDK9. So there are overloads, certain additional methods on, for example, generic application context that instead of an instance supplier actually take a Kotlin function, right? So there, underneath those covers, there are overloaded methods allowing the Kotlin usage model to be more idiomatic, which is the whole point here. And it's very, very transparent to you. Right, so that is basically the lowest level where we start having Kotlin support. There's actually Kotlin support in Reactor as well. There's Kotlin support. And in the core container, there's Kotlin support for JDBC template. There's, of course, also Kotlin support at the web framework level, in particular for the WebFlux functional API. So we're providing Kotlin support at many levels. But you get the idea. It's a core and kind of very streamlined part of the standard framework arrangement that we're shipping in 5.0. No extra jars needed, no extra setup needed. Just start using Kotlin and everything else happens by convention. All right. A topic you might already have heard quite a bit about, right? If you've been to previous sessions today in particular, or to the Kotlin session yesterday, the Spring Kotlin session yesterday, is our reactive focus. So I'm also going to touch upon it here, but coming from a different angle and kind of trying to wrap up the story from a different perspective here. So the motivation why we even go into this, it's interesting for a start, right? So why are we doing this? Well, we believe that there are requirements out there for modern web architectures that are really hard to satisfy in a traditional web stack. Servlet-based web stacks come with a lot of assumptions. And servlets are basically an abstraction. The abstraction sort of has quite a bit of baggage with it, right? The assumption that a request is being processed by being assigned a thread, processing that request in that thread, returning that thread to the thread pool. So we basically own the thread for the entire lifetime, the entire server-side lifetime of that HTTP request. This comes at a price. If you're doing blocking invocations to some data store or in a microservice architecture to some other microservice, you're basically waiting. You're doing some I/O operations and you're waiting on them to come back to you. Then you're blocking one of the threads in the servlet container's thread pool, right? One of those endpoint threads. With appropriate fine-tuning, and there's quite a bit that's possible in the servlet world. There's actually a lot that's possible in the servlet world, right? So with corresponding measures, you might get pretty far with this, but there's a limit to how far you can take it. In extreme scenarios with a very high number of clients, very strong latency involved, lots of external systems to be waited upon, in such scenarios, you might not get very predictable behavior under high load. Whereas in a reactive architecture, it comes with different qualities. You have to code differently, to architect it differently, but by its design, you will get more reliable, more predictable behavior, even under extreme conditions. So we could spend the entire hour talking about the motivation for Reactive, but an inspiration for us, of course, has been what's been called the Reactive Manifesto. I'm not a great fan of manifestos myself, actually, but it really hits a few key characteristics. The idea of responsiveness and resiliency is particularly essential here. Responsiveness even to late-coming HTTP requests in a highly loaded server, and resiliency in terms of being able to recover from almost any arrangement, any challenges that your server might have faced, even under extreme conditions. Of course, the manifesto is just a bunch of statements, right? A bunch of text. More interestingly, something that followed from it is the Reactive Streams initiative, which produced an abstraction on reactivestreams.org as a website, right? Living in the org.reactivestreams Java package. This core abstraction models a very essential part of a reactive processing stack. The interaction between resources, in particular a concept called back pressure, a kind of a level of flow control between a publisher and a subscriber in a reactive processing architecture. So reactive streams are a fundamental building block. They basically literally consist of just a couple of interfaces, just a few methods. They model just the essentials of runtime interaction in such a stack. Basically, a publisher is only going to start publishing elements once the subscriber is actually ready. The subscriber keeps taking elements. If the subscriber is currently blocked, cannot produce any further results to its output, to its clients. For example, writing back to the HTTP response stream, then it's basically going to say, thanks, dear publisher, stop pumping data my way. With this kind of model, you'll typically have an event loop backing it. So very few threads, but those threads are always busy because they are only being invoked if a step can actually be taken. You never wait on something. Basically, you always just back out and you're being re-invoked once the particular streams are ready to process further data. Reactive streams are very low level, so you're not going to work with this directly. You're typically going to use a reactive composition library that builds on reactive streams underneath the covers. And our choice of reactive kernel here and reactive API level is Reactor. In Spring Framework 5.0, we actually use Reactor 3.1 already, so Reactor already had quite a bit of history. Reactor is basically a sort of alternative to RxJava, right? It's kind of a modern-day server-oriented Java 8 baseline and reactive streams from day one composition library. RxJava already has a bit of history, predates reactive streams. It's still Java 6 compatible because of its Android user base. So RxJava is constrained by different forces, whereas in Reactor land we're really focusing on the same targets, the same purposes as Spring Framework itself. So we'll see Reactor shining through in just a moment. But let's talk about the Reactive API types first. There's a bit of confusion out there. An org reactive streams publisher, it's a very low level, very minimal API, right? But the publisher is very essential. Basically, everything that you typically interact with, like an RxJava flowable or a Reactive Flux or Mono, is a publisher implementation. But you'll typically always use a concrete implementation that allows you to actually express some concrete operations. So in Reactor, those concrete API entry points, both of them publisher implementations, are called Flux and Mono. Flux basically a sort of open-ended stream of a sequence of elements, and Mono just a single element or none. So if you, in traditional RxJava 1 speak, that would be observable versus single, basically. Or a completable future is a sort of variant of Mono without back pressure, right? You could argue. Or if you want another comparison that I put in here is like in the non-reactive world, right? Java util collection streams. Well, there's a stream and there's Java util optional, right? The same kind of idea. Sequence of elements, single or none. And in RxJava 2, it's flowable or maybe. There are plenty of those types out there. They all have their role. And they are all actually supported in Spring Framework 5's WebFlux framework, right? So in annotated handler methods, you choose to design your methods with a particular API. You may choose to follow our recommendation of Reactor and use Flux and Mono API types. You can also choose RxJava 2 types, RxJava 1 types, and to some degree, even completable future. So essentially, the WebFlux framework that I just mentioned is our reactive web stack in Spring Framework 5. Another important piece of clarification. Spring Framework 5 comes with two distinct web stacks. There's the traditional Spring MVC stack, to be seen on the left here, and there's what we call Spring WebFlux on the right. Both of them share a lot of design. They are aligned to quite some degree. They can be used with a very similar endpoint model on top. But they are separate stacks with distinct characteristics, kind of their own strengths and benefits, right? The Spring MVC stack, Spring Web MVC, remains servlet-based as it always was. If you have existing Spring Web MVC-based code, just keep using Spring Web MVC and literally the Spring-Web MVC module on Spring Framework 5. And everything is servlet-based, your choice of servlet container underneath the covers. The servlet API shines through to the usage model, right? To your components. Your handler methods may even declare HTTP servlet request or HTTP servlet response arguments. Very clearly servlet-based. Over here, there's WebFlux. WebFlux is based on a Reactive Streams foundation and Reactor as a kernel. So it's based on Reactive Stream interaction model and an event loop underneath the covers. No servlet API shining through to any higher level in particular. There may be a very similar usage model on top, like our annotated controller request mapping model that can also be used on WebFlux. But it's adapted to this reactive runtime underneath the covers and has to live and has to be designed for reactive interactions. So it may look similar, but it's not as similar as it may look, right? Because a Spring Web MVC controller typically does blocking things. It calls a JDBC operation, it triggers a JPA operation. If you're designing for Spring Web MVC, that's totally okay. Thread bound transactions, no problem, right? JPA, JDBC, no problem. Stay on Spring Web MVC, essentially. But if you can use a reactive data store, reactive HTTP clients talking to other services of yours, if you can compose your web endpoints to use non-blocking APIs underneath the covers, then WebFlux becomes interesting. Maybe you've already got a data store driver. That data store driver is maybe RxJava based, returns RxJava observables or an RxJava 2 flowables to you. You can expose those to the Spring WebFlux stack directly. They are a natural part of a reactive web endpoint model. So there may be many reasons, but my favorite perspective is this bottom-up perspective. You've got reactive data stores and reactive, like HTTP client APIs, for example, for your other services that you need to call. So from that bottom-up motivation, you might want to design a Spring WebFlux-based arrangement of web endpoints that are reactive from the bottom, basically from the data store level to the HTTP endpoint level in order to reap the full benefits. So what does this look like in the annotation-based world? A reactive web controller initially looks very similar to a Spring MVC controller. You actually have, even now, I usually have to look twice to see the difference because they're using the same structure, controller endpoints, controller annotation, mapping annotations, get mapping, post mapping, and co as commonly used in Spring Framework 4.3. But what the methods actually do is different. Those methods here seem to call this, basically just a sketch, right? They seem to call an API, some repository, but that repository doesn't load the user. We ask for a user by ID, but what we get back from the repository is a mono of user, a reactive type, right? We're basically getting a handle that is capable of loading the user for us, a Reactive Streams publisher being able to publish that user. We are passing that back to the Spring WebFlux stack, and the Spring WebFlux stack knows when to invoke it, right? Once the HTTP stream interaction is ready to actually handle the outcome of the rendering that we need to do for that user object, then and only then we're going to trigger that publisher, take the object, send it through the codec step, and render it out to the HTTP response with a full backpressure model running in an event loop. So the getUser method represents a single user or potentially none. That's why we chose the mono representation here. Get users asks some repository underneath the covers here to load all users, can be any number of. So we're using Flux as the representation. Of course, you just at this very point, you could declare public flowable of user, now Java 2 flowable. The Spring Web Flag stack natively understands what you mean, right? It understands Java 1 and Java 2 types that you return from those endpoints. For example, because your repositories or your client API that you're using natively returns Java types, you can just pass them through. We adapt them for you. So annotation-based controllers are structurally similar, but they are designed for a reactive world. They are meant to essentially return Reactive Streams publishers for the particular response that they are about to produce. An alternative model that the diagram hinted at before is what we call router functions or functional web endpoints. So router function has an entry point. This is a different way of consuming, of tapping into our reactive web stack. So instead of using the annotation-based model and the dispatcher handler that understands those annotation-based mappings, instead of that, we use a very straightforward functional setup, functional API that we call router functions and handler functions. So if you look at this little piece, it basically models the same endpoints as the annotation-based slide before. It says, once a /user/some ID request comes in, dispatch this request to handler delegate getUser, a Java 8 method reference, which is this method down below. And for another route, if just /users comes in, let's dispatch to the getUsers method. Both of them need to implement handler function. Handler function is a server request going in and the mono of server response going out. So for Java 8 method references to work, and this is what we intend to do here, we need to follow we need to comply with that signature, right? That's why both of them have the same signature. There's no annotation-based model here. You can't do add request param, no flexible signatures, sorry. In the functional world, there's a strict, cleanly defined API, and you have to comply with that API. So what do those do? Like the find all method, for example, loads its flux of user and then programmatically builds a server response, says status OK, here's the body, the publisher for the body elements. And for the codec step, it's Java 8 after all, and Java after all, no reified generics, right? We need to pass in the user class to tell up front that it's supposed to be converted to a user. For getUser, there are several ways of coding this, but essentially you're asking the request to extract the path variable ID. You're converting that ID to a long because it's natively a string representation, and then you dispatch to your repository, find by ID with the number, and you return the mono of user coming back from this. Then you build a server response for it. In a functional API design or a Java util collection stream style API design, this is a very natural thing to do. So this is the method reference variant. Might look a little bit alien. Maybe this looks less alien. This is the very same code, just using Java 8 Lambda expressions, right? Inline Lambda expressions. So the router says route user's ID, and here's the same code, but now in an inline Lambda. The signature disappears, which is nice, right? Request coming in, produce the server response. And for the other route, same idea, right? So the signature going out of your way. The functional model sits in parallel to the annotation-based model, right? So it's your choice of how you'd like to consume the web flux facilities that we're providing to you. The annotation-based model is, of course, very nice for a higher number of endpoints that you want to pick up in a distributed fashion from several places all across your code base. The annotation-based model has lots of benefits, the flexible signatures. But for a smaller, more microservice-oriented unit, just a few endpoints that you're modeling, 2, 3, 4, 5, maybe 10 endpoints, this sort of Java-based DSL here can work really fine. In particular, if your web endpoints essentially just delegate to some code underneath and adapt a few parameters. So it's a totally different way of coding the routing information and the handling information for your web endpoints, but uses the very same facilities, the same codecs, everything else underneath the covers. And for the sake of timing, we're not going into Kotlin examples today, but you may imagine there's, of course, a Kotlin extension for this style of DSL, and this is particularly sweet when being used with Kotlin. Has actually been shown in the Spring Kotlin talk yesterday. Last but not least, quick reference, because it's often forgotten. We also ship a Reactive Web Client, an alternative to REST template. Because REST template essentially is a kind of blocking style interaction API. We have a new web client, stylistically very similar to the functional web endpoint model on the server side, that you can use to build an HTTP interaction from the client side. And since it's the same style of API design, what you typically get out of it is a Reactive Streams publisher, a Reactor Mono, or a React Flux. The same kind of idea applied to the client side of an HTTP interaction. So that's also part of the WebFlux module to provide a very complete picture. So there's Spring Web MVC and REST template basically, and there's the Spring WebFlux server-side model, annotation-based, the functional API model for WebFlux, and there's also a functionally styled Reactive Web Client in WebFlux. All right, so much for what I intended to show in this tour today. Thanks for your attention. Just quickly summarizing that all of the aforementioned features and design variants are available in Spring Framework 5.0 GA, so 5.0, which is GA since September already, with the baselines attached. If you're on JDK8 and on a recent servlet container, you could just straightforwardly upgrade your application from 4.3, for example, to 5.0. If you have existing Spring Web MVC code, try the upgrade on WebMVC first. If you'd like to try to familiarize yourself with WebFlux, be our guest, right? Now's a great time to try this. There are many pieces in place. Not only WebFlux here in Spring Framework itself, there's also Spring Data K, our Spring Data sister project with its repository abstraction, having a reactive repository variant for all data stores that actually support reactive drivers underneath. For example, MongoDB and co. So there are many pieces in place. Spring Boot 2.0, of course, wrapping up Spring Framework 5, taking Spring Data K, combining them into its world, is about to go GA towards the end of this year, also with a full reactive story, right? But it's one usage model. It's still your choice. Even in Spring Boot 2.0, it basically provides all of its facilities, either in the servlet-based web stack world or in the reactive web stack world. And as mentioned, start thinking from the data store level, right? If there's a reactive data store, a reactive driver for your data store, that might be a strong motivation to try the WebFlux stack. If you keep using traditional JDBC drivers or JPA, other blocking APIs, stay on WebMVC. Don't even think too much about it. There are ways of combining those things, right? We have some support for reactive publishers, Reactive Streams publishers, even in WebMVC. We are adapting this to the Servlet 3.1 async stream model. So if you have a reactive driver for a certain part of your service, you can even expose this in Spring WebMVC. There are many ways of building combinations of those stacks according to your requirements. In WebFlux, which we haven't explicitly mentioned yet, you also have a choice of providers underneath. You may, for example, choose to use Netty as the most capable networking library out there. But you may also use Tomcat or Chetty or Undertow Core. So WebFlux actually comes with a choice of HTTP engines underneath its Reactive Streams-based architecture. And you might wonder, Tomcat, Chetty? I mean, add those servlet containers? Why can I use them underneath WebFlux? Well, Tomcat and Chetty are fundamentally HTTP servers, HTTP engines. If you're using them in a reactive stack, you're not using them as a servlet container. You're using them as the HTTP engine for a reactive web stack. And in particular on Tomcat, where we have several Tomcat committers in our wider team at Pivotal, in Tomcat there's a lot of work that specifically went into improving Tomcat's suitability for reactive web stacks. The Chetty guys are really interested in alternative usage models for their core HTTP engine. In Undertow, there's even a separation of Undertow Core and Undertow Servlet. If you're using the reactive web stack, it works with Undertow Core directly. There's no need for the Undertow Servlet bridge. And of course, Netty remains everybody's darling, right? If you're the most capable, most customizable, most tunable networking stack out there, of course, is Netty. So for this choice of containers, we're not making a strong recommendation, but Tomcat and Netty might be good starting points for a start. Basically, make your pick or follow Boot's pick, Boot to the Dose pick in that respect. So don't be scared. There's a lot of power waiting here, a lot of choice, and a lot of power that comes with it. I hope you're enjoying the power that we're giving to you here, and let us know how it goes and how those things make sense in the particular architectures that you're designing. Thanks for your attention. Enjoy the rest of the show.